Great. Thank you very much. I appreciate it. Clark mentioned, my name is Jamie Jacob. I'm a professor in mechanical and aerospace engineering and director of the Unmanned Systems Research Institute here at OSU. I want to talk briefly about operating unmanned aircraft systems, aka drones, at OSU. Rules, regulations, and different ways to get involved if you're interested in this type of application for your research. Brief agenda. I'll talk a little bit about what a UAS is and a drone, so we can define what the system is and the different components of that. And we'll spend a good deal of time talking about the different applications as well. Really just scratching the surface of what you can use a UAS for. We'll spend a little bit of time talking about the rules, namely how you navigate within the national airspace. Drones are aircraft, and so we have to follow the same rules that other aircraft do as well, and how you become a drone pilot under the Federal Aviation Regulations Part 107. From that, we'll also talk about the flight rules on campus. If you're interested in flying on campus, what you have to do to make that happen. And then I'll also talk a little bit about USRI, primarily what USRI does and how you work with USRI. And we'll end with an FAQ. I'll start with a brief video and some historical context about this. This is a Dutch restaurateur, and every year he likes to take the first asparagus crop and deliver it from the field to his restaurant in a new and novel way. And several years ago, he did this using a drone. And I utilized this video to show that not all applications are necessarily well suited for drones. You'll notice here that they have to follow it in a truck. And then when they're taking off again after having to switch batteries out, it results in a crash. And you can see some of the hazards here, which we won't even have time to get into in terms of potential effects from drones crashing, catching on fire, due to the batteries that they're used here. So this is to say that there's a lot of really useful applications for drones, but not everything necessarily requires a drone or is best suited for a drone. And even if it is, there's a lot of hurdles that you have to overcome in order to be able to implement that. I like how he's trying to put out the fire there by blowing on it. And that kind of helps frame the context of this presentation, which is we're going to be talking about drones, but always keep in mind a drone is just a tool. And like any other tool, sometimes there's going to be a good use for it. Other times, not so much, but you have to know how to use that tool. So first off, what is a UAS? And there are lots of words and abbreviations for this. The most common one now is unmanned aircraft system. You'll also see this referred to as uncrewed aircraft system, but historically this has gone by a number of names: remotely operated aircraft, remotely piloted vehicle, unmanned air vehicle, modern aircraft, remote control aircraft. We're just going to call them a drone to simplify things. And so I'll refer to these things as either UAs or drones, kind of back and forth. It's all the same thing, where we have some system, some aircraft that does not have a person on board, and that operator is remotely operating the aircraft. There may be some autonomy or limited autonomy with the actual aircraft operation, but you still have all of these components, namely the aircraft itself, a ground control station, some kind of communication system that allows you to communicate with the aircraft, and then the actual pilot. Just because we say it is unmanned or uncrewed does not mean that we don't have a pilot involved. There's always a pilot involved with an unmanned aircraft. And specifically, we're going to be talking just about SUAS, which is known as Small Unmanned Aircraft Systems, which are defined by the FAA as any unmanned aircraft less than 55 pounds. So that may sound relatively small. 55 pounds is still a pretty big drone for most applications. And for 99% of the stuff that researchers at universities are going to do, SUAS will fit the bill. And you can see there are a lot of different types of systems that fall under the SUAS category. used for a number of different applications. These could be fundamental research, they could be remote sensing, something along the lines of a payload delivery. You can use them to study aircraft performance, such as aerodynamics, flight control systems, or aircraft autonomy. All these types of platforms, regardless of the fact that they look very different, some of them are fixed wing, some of them are traditional helicopters, some of them are multi-rotors, all fall under this unmanned aircraft category. Now, there are a range of different types of vehicles. We'll talk about the differences between them and their ranges of different costs. Much of the current UAS systems that can be purchased are really driven from the hobby industry, where these systems have really grown out of the remote control or model aircraft enthusiasts. And so you can buy these systems that are fairly capable for relatively low cost, in the order of thousands of dollars. When you start to get into the more professional systems that typically might be used for such things as cinematography or high-end research applications, then the price may go up substantially. These systems tend to be a little bit larger, a little bit more robust, and have much more autonomy built in order to be able to perform their job that they were designed for. And we'll go over differences between each of these systems. Now, there are lots of applications. Again, we're not going to go through all of these. I'll provide some remote sensing applications. It's not the goal of this particular talk to talk about how these systems are being used in different applications. That's really up to you as a researcher to figure out how you can use the systems in order to be able to improve your really data acquisition process, because that's what the systems are, a way to get data in a more expeditious or efficient fashion. But there are a number of practical applications that these systems are currently being used for by both government and civilians, as well as commercial applications, and their use is just going to grow as their capabilities increase as well. Now, as I mentioned before, there are basic 4 components to any unmanned aircraft system. The first of that is the one that we usually think of, which is the vehicle, that component, the aircraft itself. And it could look like a very traditional aircraft with a propulsion system, a fuselage, wings, control surfaces, or it may look more like a helicopter or multi-rotor. Doesn't really matter. That fits into how the vehicle is going to operate, as well as the performance of the vehicle. But there are 3 just as important components to the entire system. The first of those is the autopilot, which essentially does that second-to-second or minute-to-minute control of the vehicle. And that autopilot can be, very rudimentary, where it's just keeping the vehicle stable, and it's still requiring pilot input to determine where it's going, or it can be very autonomous, where you're essentially pushing a button and the vehicle is following some kind of predetermined trajectory. So these modern autopilots can be very capable, and the cost of those autopilots has come down substantially as the performance of microcontrollers and capabilities of the systems of MIM systems has improved over the last decade. The second piece is the ground control station and the comms. This could be as rudimentary as a handheld transmitter, allowing the pilot to control it. It could be something along the likes of an iPad or tablet, or it could be a full-blown computer that you're using, such as a laptop shown here in the field, to be able to do that remote operation. The last component is the payload. And you may not think of this as an important piece of the whole UAS, but without the payload, the UAS really has no job. The whole purpose of the vehicle is to be able to carry a payload to perform some kind of mission. More often than not, that payload is some kind of camera. It could just be a regular visible RGB camera. It could be taking still pictures or video, or it could be an electrical optical infrared system. But it could also be something like a LiDAR or an in situ chemical sensor. We're not going to talk a lot about the payloads today. I'll talk a little bit about EOIR systems and what they can be utilized for. This is really what's driven from the research application, which is, well, what kind of data do I need to acquire, and what's that payload look like? And then make the determination, is the UAS or a UAS the best option in order to be able to get that data? So we'll talk a little bit about UAS pilots, and we'll come back to this when we talk about part 107. But when we think about UAS pilots, we think about, well, what do you really need a UAS pilot to look like? And the question right now is still very open. There are lots of ways that you can operate UAS, but we'll use kind of the military approach, and they've taken essentially two separate tracks. One on the Air Force, which is they say, well, we're taking Air Force pilots that pilot manned aircraft, or the Army approach, which is, hey, we're going to really look at this from the standpoint of using video game-like controls to be able to operate those vehicles. And so you end up having a very different paradigm in how these systems are being controlled. Now, the shift or the difference between this is also really due to the types of vehicles. The vehicles on the left tend to be multi-million-dollar, very large aircraft, while the vehicles on the right tend to be much smaller, much less expensive, and therefore much less dangerous to operate, but also much less costly if you lose that in a crash or an accident. But as the electronics and systems become more capable, we're starting to see a much greater shift towards this right-sided paradigm where, we're using relatively simple controllers in order for us to be able to direct the vehicle to do a particular maneuver or mission, and the second-to-second control of the vehicle is being handled by the autopilot. Now, there are also different approaches into how we develop or utilize these autopilots on systems. And as a typical university, it's very common to use a mixture of both off-the-shelf and custom in-house components. And there are really three different paths that you can take for the autopilot and ground control station. The first of those is hobby systems. These are systems that have been really, again, developed from the hobby industry, relatively low cost, using a lot of open source software in order to be able to do that flight control. And then you have to go through the process of integrating these into your vehicle. These have become really capable. The systems that are shown here, like the Pixhawk, the Orange Cube, these are systems that would have cost six figures 20 years ago, but now you can purchase these for several $100s, and they are very capable. Then you have professional systems, which might be certified for flight within the national airspace aboard much larger aircraft. They typically have gone through much rigorous quality control. The components tend to be much higher quality, but the architecture and the software might be closed, so you might not have access to it. So this may not be the best approach for researchers who are interested in modifying some of those onboard source code. The last option is to build one yourself, and these are possible now using things such as Raspberry Pis, BeagleBones, Latte Pandas, other microcontrollers, which are very, very capable. Then you can use some of the either open source software that you can import to the system, or you can control that yourself. Now, what I tend to think of these for each one of them is for the hobby systems, you get what you pay for. It's relatively low cost, but they tend to have a much higher failure rate than you will with the professional systems, which cost a lot of money. So you pay for what you get. And of course, if you're building your stuff yourself, well, you're never quite sure what that's going to look like until you go through lots and lots of testing. Now, the control of the systems, again, have a wide variety of different options based upon what you're using. As we've seen from things like Predators and Global Hawks, very large aircraft that are the size of commercial airliners in many cases, they tend to have a very cockpit driven like control system. But on the hobby side, these are also driven by consumers, where you have these hobby grade like controllers that are the predominant form of control for the aircraft. What we've seen over the last several years is these essentially being driven to more of a tablet-based control, where again, you're doing less second-to-second pilot of the aircraft, and you're really focused on providing the waypoints or the trajectory of the vehicle, and the vehicle is then determining the best way to get from point A to point B. Now, as an example of that, here's a flight that we did just yesterday at the Oklahoma Transportation Research Day. You'll notice in the foreground, one of the larger vehicles that we have with an EOIR camera on board that's used for a number of standard missions to be able to get imagery. But you'll notice in the background, you'll see a fixed wing vehicle that will actually take off in a VTOL mode, vertical takeoff and landing, just using a tablet. So AJ on the right-hand side is actually controlling the vehicle. He's given it the waypoints. The vehicle will actually autonomously take off once he gives the command for this. So you won't be able to see it transition into fixed wing flight, but once it gets to altitude, it essentially pitches nose down 90 degrees. And then from there, it performs its waypoint navigation until it completes the mission, comes back, and again, lands autonomously. Now, what you will notice, and this is something we want to emphasize today, we have our pilot in command here, AJ, first off, wearing a vest that identifies him as a member of the flight team, and he is maintaining eyes on the aircraft. So he's able to see the aircraft throughout the entire flight, which is really, really important because he's operating this aircraft in the national airspace. There could be other aircraft that may come into the area, such as an emergency helicopter, and it's up to the pilot to be able to control that unmanned aircraft to avoid the manned aircraft that might be have an incursion within the airspace. Now, a general comparison between the platforms, we have two basic types of vehicles. One of those is fixed wing, the traditional aircraft, and the other is a rotary wing, which we tend to think of as a helicopter or multi-rotor. The fixed wing generally has better performance capabilities in terms of range, endurance, the weight of the payload, how fast you can fly, but it also tends to be a little bit more difficult, and you have to be able to get up to speed before it takes off. So it may require a runway, a hand launch, or some type of catapult recovery system, particularly if the platform is above 10 pounds. With a rotary wing, it's essentially, powered lift in this case. So your rotors that you have on the vehicle are always providing that aerodynamic lift, as opposed to the wings in forward flight for a fixed wing vehicle. It does have the advantage of vertical takeoff and landing, so it's much easier from a logistical standpoint in order to be able to take off and land. And it's well suited, since it has this hover and stare capability, to be able to take imagery. And you'll see two examples here in the picture. One is a standard off-the-shelf system that's taking images or video, and the other is another vehicle that's been instrumented with a number of diagnostic equipment in order to be able to measure atmospheric characteristics. So you can also merge these two and have a hybrid system that's either the best of both worlds or the worst of both worlds, depending upon how you're looking at the problem. And you saw that in the previous video, where you have a fixed wing system that also has a vertical takeoff and landing capability. Now, each of these systems have a different roles. It really depends upon what you want to do with the vehicle. If you're looking at a relatively small area, then something like a rotary wing vehicle is a good option. If you're looking at a larger area, then you scale your system up to a larger platform. And if you want to observe or perform measurements over a large area, then you typically go with a fixed wing system. It really just depends on what your end goal is with your experiments that you need to perform and the data that you're looking at. The capabilities tend to increase with platform size, but so does cost, complexity, and therefore risk as well. And that's the reason the FAA has really developed this less than 55-pound rule for SUAS. Once you get above that, the systems become much more dangerous if an accident occurs. But UAS themselves can range from systems that are less than 250 grams up to thousands of pounds, right? And so you can have UAS that are just as large as a airliner in many cases. Now, most UAS are going to be utilized for remote sensing, not completely. And so you can put other sensors on board. And, we use those very commonly in our laboratory. But more often than not, the general use of a UAS is going to be for remote sensing applications. It carries some type of camera on board. So it's useful to look at the different regimes that you have in terms of remote sensing. You have ground observation, which is using cameras directly on the ground, low altitude aircraft, which are less than 10,000 feet, high altitude aircraft, which typically are going to be manned aircraft above 10,000 feet, and then satellites, which have altitudes 150 miles and up. UAS fall within that low altitude aircraft category. So there are advantages in terms of being able to operate aircraft much more closely to the ground, but it also means you can't carry or cover as much area since you are closer to the ground. With the same field of view, you're not going to be able to see as much land. So what airborne imaging really gets you is that different perspective. And since these are being used for crop sensing quite a bit, I'll use those as some examples. So when you get off the ground with UAS, obviously it provides you that bird's eye view perspective of being able to look at the data directly from the top. And the benefit of the UAS, furthermore, is that you're able to get relatively close. It performs a similar type of mission that you have with manned aircraft that have performed observations in the past, but you can have a camera that's almost as good as what you have on a manned aircraft, but since you're much closer, you get much higher resolution. And that's the real advantage, is you're able to get more data at a much, much lower price point because you can operate a manned aircraft on an hourly basis that's going to be the total cost of your UAS. So there's a great advantage, and it opens up many new avenues for researchers to be able to use these systems to be able to gather data. Now, you'll often see EOIR used as the imaging acronym. That just means electro-optical infrared. So it gives you the capability to view not just in RGB, but also in infrared and sometimes hyperspectral or multispectral modes. We're able to look at a number of different bands, and you can combine those bands to be able to tell you something interesting or novel about what you're looking at. More often than not, this is going to be organic in nature because those, due to the way that you have reflectivity from the different organic plants or animals, you can use that to assess things such as health. But you can also, very helpful, IR, for example, sees through smoke very well, but doesn't see through water. So there are advantages and disadvantages to each one of the bands that you have, that you may have on a camera. So those EOIR applications can be used, again, for a number of different uses for both natural and physical sciences, things such as tracking flood, wildlife tracking. You'll notice here you can actually see the tracks from wildlife, or using the IR system, you can actually make observations at nighttime and to be able to pick out animals just from their heat signature. Now, multispectral systems are widely used for crop sensing because if you are able to image over multiple bands, not just RGB, but also UV and IR, you can determine a lot about crop health. So this is used pretty substantially. And what you'll notice in the past, the image up on the upper left is provided by Professor Paul Weckler in Biosystems and Ag Engineering. You'll notice this is an EOIR system mounted on a manned aircraft. And I provide this as an example because prior to 10 years ago, this would have been your only option. If you wanted to get airborne imagery using a sensor, you would have had to figure out how to mount this to a manned aircraft. And it would have required a lot of cost and expense because you have to go through a certification process when you're making modifications to the aircraft itself. So now, since both the EO/IR systems have gotten smaller and more capable, and we can mount these to drones, you can marry those together and then skip this manned aircraft process. It doesn't mean that manned aircraft are no longer used. There are many applications where it still makes sense to use these much larger vehicles that fly at much higher altitudes and carry much larger payloads with them. But here's an example of a near infrared image in false color. You can very distinctly see the crops, which are radiating lots of heat, as opposed to things such as the roadways. And so it's very easy to tell the differences between where you have growing living things and where you have buildings, roads, and also in this case, water. You'll notice that it appears fairly black here. Now, if you're able to take those different bands, you can actually combine them together to, again, provide you an assessment of things such as crop health. And this is commonly done just using the red, the blue, the green, and the infrared band for the NDVI process, or you can use hyperspectral bands, which provide you multiple bands of the infrared, far, mid, and near infrared, as well as ultraviolet to be able to tell you even more detail and information. And from that, you can back things out, such as overall plant health using this information. There are other systems you can use as well, such as LiDAR, photogrammetry. Those are systems we're not really going to go into today. Photogrammetry itself is probably worth an entire another data bytes lecture just to go through that process. So that's something we might explore in the future. But things such as looking at biomass using LiDAR systems, which allow you to map out in 3 dimensions the structure of not just the land, but also things such as plants. And then when you combine that with EO/IR systems, you can not only get plant mass, but you can also get plant health. And that tells you a lot, not just from a standpoint of plant and soil sciences, to be able to understand that overall quality and quantity of plants, but also things such as fuel sources for wildfires. Now, going back to the basic operation of the system, as I mentioned, we have the unmanned aircraft itself, which carries some payload on board. We have that ground control system, which again might be a computer, could be a phone, could be a tablet, could be a standard controller. And then you have a communication system that allows you to communicate over long distances with the actual vehicle. Now, sometimes that can be a direct telemetry. Other times that can be actually going through the cell phone network for that communication itself. And then that vehicle is, of course, doing some kind of observation of monitoring on whatever asset it is that you're looking at, whether it's livestock, crops, wildfires, infrastructure. That's really irrelevant to our discussion today. Now, over time, the FAA has started to open up the airspace. 7 years ago, we were still very limited in how we could use these UAS, and we had to go through what was called certificates of authorization in order to be able to perform flights. In 2016, the FAA opened up what's called Part 107. So under the FAA's CFR, that allows you to become a UAV pilot, getting a Part 107 pilot's license. And over time, the FAA started to open up those airspace rules to allow you to get what are called waivers to the general Part 107 rules, which basically say you can only fly under 400 feet under visual flight rules in one aircraft. And now you can fly at higher altitudes, operate more than one aircraft, and fly, for example, during the night. Or over people, or operate more than one aircraft. So over time, the FAA has started to open up the airspace to allow a greater use drones in different operations. Now, this has essentially expanded from this paradigm that we talked a little bit about earlier, where we go from a direct control operation where the operator is essentially commanding what the vehicle is doing throughout the entire flight. So even with something like a fairly modern drone, this is still pretty common, where you're commanding the takeoff, commanding it to go to a certain altitude, and once it climbs to that altitude, cruise to the target. You're controlling what the vehicle is doing during its mission as it's, performing recording of its target or getting that data, coming back, descending, and then landing. And that's still possible with almost all vehicles, is having that direct flight control. Now, as the autopilots have become more advanced, you can start to send these vehicles out farther and farther away, something called beyond visual line of sight. And a beyond visual line of sight operation means that you can no longer see the vehicle. Now, what becomes problematic with that is just because since you can no longer see the vehicle, that also means that you may not be able to see other aircraft that are operating. And first and foremost, the FAA is concerned about keeping the airspace safe. And if you can't see the vehicle, you may not be able to see another aircraft that might be having a collision, a possibility with that aircraft. So you have to be able to see that. Now, the FAA is starting to open these up as well, as long as the vehicle has other types of broadcasting capabilities on board, such as remote ID or ADS-B, or you have other ways to track the aircraft. Now, eventually, we'll get to the point where we have full autonomy. Now, this is possible right now, but it's not 100% reliable. And that's why we're not able to do this yet. But at some point in the near future, you'll be able to operate the aircraft essentially sight unseen, since primarily you will not care about the aircraft operation, you'll care about the data that the aircraft is actually acquiring. Now, I'll talk a little bit about airspace operations and pilot requirements, focused on pilot requirements first, and we'll come back and talk about the actual airspace itself. Now, the UAS operations within the U.S. Are governed by what are known as 14 CFR Part 107, and we'll just refer to this as Part 107 or the small UAS rule. This requires that you have a pilot in command, which we'll refer to as a PIC, with a Part 107 license. To operate a drone, you need to be licensed by the FAA and have that pilot's license. The vehicle must also be registered. So there's a website, the FAA Drone Zone at the FAA, that allows you to go and register a vehicle to give your vehicle a unique number, and then you have to put that registration number on the aircraft. If you're doing this purely for recreational, it does not include if you're doing this for any type of research activity on the campus. Recreational really only counts if you're doing this for fun. Even then, you have to follow and pass a test called the Recreational UAS Safety Test, which is pretty straightforward on the FAA site. And you have to follow the recreation rules, and you still need to register your aircraft. Now, there are a lot of rules here for Part 107. I'm not going to go through all of them in detail, but we'll try to run through these pretty quickly. First and foremost, you can operate in the daylight under what's called Visual Flight Rules, or VFR, in Class G or Class E airspace. And we'll define what Class G or E airspace is in a minute. As we mentioned, these are for small UAS, so the vehicle must be less than 55 pounds. It cannot be 55.0 pounds. It must be 54.999 pounds. Once it reaches 55 pounds, it no longer falls under Part 107, but you can get waivers and exemptions for heavier aircraft. Flights are limited to 400 feet altitude above ground level or 400 feet over structures. And we'll give an example of what that means as well. You must be 5 miles away from the airport, stay out of airport flight paths and restricted airspace areas, and obey any FAA temporary flight restrictions, or TFRs. For example, that would include NCAA games. So football games at OSU have TFRs. So you're not able to operate before, during, and immediately after a football game. So that's a restricted area. The small U.S. operator must always see and avoid unmanned manned aircraft within the area. That means you need to be able to see the airspace. And if you have any aircraft that come into your airspace and there's a risk of collision, you must take action. And typically that means landing the aircraft or at least performing an avoidance maneuver to make sure that that airspace remains safe. You must also discontinue the flight when continuing to pose a hazard to other aircraft, people, or property. You can't fly over people. If something's happening with the aircraft or appears there's some kind of malfunction, you need to be able to take immediate action and land that aircraft. You must also assess weather conditions, other airspace restrictions, and location of people to minimize potential risk to those on the ground. And you may not fly over people except those directly involved with the flight, meaning you can't fly over a crowd. Now, as I mentioned, with the airspace operations, we'll come back and define what each one of these means. Operations in Class B, C, and D, which are around airports. Stillwater Airport, for example, is a Class D airspace. Tulsa and Oklahoma City airports are Class C airspace. Dallas would be Class B, are allowed if you get permission from air traffic control. Essentially, you have permission from the tower. You can operate aircraft in Class G airspace, however, without ATC permission, meaning you can just go out and fly without letting the FAA know where you're operating at. Now, to be what's called a remote pilot in command, you must have what's called a remote pilot airman certificate. That means you take a test, you get your license, the FAA email or mails that to you, and you have that card such that if you're ever flying, you can demonstrate to authorities that, yes, I am a licensed UAS pilot. Now, you don't necessarily have to be licensed if you're operating the aircraft if you have a PIC to serve as that direct supervisor. So, for example, if you want to fly an aircraft for a project, but you don't have a Part 107 pilot, then you can find a Part 107 pilot, for example, from USRI, to be able to perform that PIC role for you. You do have to pass the test, and there's certain qualifications for that. It's a fairly straightforward test, but if you're not familiar with airspace or things such as airspace operations, aviation charts, then it does require a little bit of studying in order to be able to pass that. You also have to go through a fairly simple TSA check and be at least 16 years old. Now, typically when we're operating aircraft in the field, we tend to divide these roles into one of three. One is a flight director who's really in charge of operating the mission and making sure that the mission is successful, maintaining what we call a secure or sterile cockpit, meaning the pilot isn't being bugged by passerbys or spectators that want to ask questions. The pilot really needs to be able to focus on the safety of the airspace. You have the vehicle operator, or the pilot in command, or PIC, who's focused on the aircraft control itself and making sure that the aircraft is operating correctly and maintaining safety of the airspace. And then you have the payload operator, who really just cares about the payload and making sure that you have operation of the payload. And so you can see some examples of that here, where we have a pilot, a flight director, and a payload operator here, all operating from laptops and computers, being able to control the aircraft, as well as focus on what the payload is observing. And likewise, out in the field here, you have a payload operator on the right and the vehicle operator on the left, and then the PIC itself is the one taking the picture. Now, this can be varied. You're not always going to have multiple people to be able to do this operation. But this is a recommendation primarily to focus and think about the aircraft from the standpoint as being an aviator. You're operating a vehicle, you want to make sure you're operating safely. So we'll talk a little bit about airspace operations now from the aerial navigation standpoint, primarily talking about airspace itself. Now, there are operating rules that you essentially have to follow when you have the vehicle operating within the national airspace. You have to follow under visual flight rules, so visual line of sight only. So you have to be able to see the aircraft. There are waivers to this where you can get what's called extended line of sight or beyond line of sight. The extended line of sight allows you to not necessarily see your aircraft, but you're still able to see larger aircraft within that airspace. It's particularly useful if your drone is fairly small. You must have 3 miles of visibility. So, clouds, rain, fog, that will impede that and restrict your ability to fly. Daylight or civil twilight. So that's 30 minutes before and after what we tend to think of dawn and dusk, respectively. No operations over people that aren't directly participating in the operation. And you must yield right of way to all aircraft operating within the airspace. And you cannot interfere with airport traffic flight control patterns. So if you don't want to be operating near airport where aircraft are coming in and landing, because that's really the most dangerous portion of the aircraft flight. Without a waiver, you can only operate one aircraft per person and a max ground speed of 100 miles per hour. So that allows you to maintain some control over what the aircraft is doing. Now, you can have external payloads on your vehicle as long as the payload does not adversely affect the flight controls and it's secure such that it's not going to fall off of the payload. Now, what's interesting, you'll notice this little picture here with the UAV performing a film roll. It was really the cinematography in the film industry that drove a lot of these early rules because prior to this, most of these aerial shots were being performed by manned helicopters, which had to operate very close to the ground. And it resulted in a number of tragic helicopter deaths just due to the fact of the hazards and the dangers of operating these systems really close to the ground. So these rules were put in place really to help save lives and perform this role for the film industry. And so we have them to thank for it in terms of the capabilities and our ability to operate within the airspace. There are other things such as, you should perform a pre-flight inspection. You shouldn't do an operation from an aircraft, but you can now do it from a vehicle. If you're operating in a sparsely populated area, you can get around some of these rules. You don't want to carry hazardous cargo. I mean, these aircraft, again, tend to have a much higher crash probability than the manned aircraft. And so you have to be really careful in terms of the types of payloads that you're operating with. And as with all aviation rules, right? So you essentially have 8 hours, going from the cockpit or from the bar to the cockpit before being allowed to have any drinks. Now, there are a number of waivers that you can get that are permitted under Part 107. One of those is operations from moving vehicle or aircraft. And so you can get a waiver from that. So that way you can fly a vehicle from a moving car. Various operations outside of visual line of sight, visual observers, what we call swarms, or operating multiple or one-to-many aircraft. So that way you can have one controller operating, several vehicles. Operations over people, flying in certain airspace, et cetera, et cetera. So there are a number of different waivers that you can get to fly under different conditions. Flight over 400 feet, for example, flight under nighttime conditions. So I won't go through all these. If you're interested in a particular waiver and you'd like to know more about it, just ask me. So let's talk a little bit about airspace. So the FAA does divide airspace into different what's called classifications. We don't have to be worried about Class A because that's 18,000 feet and higher. So it's very unlikely that we're going to be flying our UAVs up to that altitude. Then you have Class B, C, and D airspace, which are large, mid-size, and regional airports, respectively. So I mentioned earlier, Class B is similar to Dallas-Fort Worth. Class C would be Tulsa or Oklahoma City, Will Rogers, Tulsa International Airport, and Class D would be Stillwater, when the tower is operating, and Class E when the tower is not operating. What you'll notice, they have what are called upside down wedding cakes, where this radius of airspace increases in size the higher altitude you get. And that essentially allows you as an aircraft operator to be able to come in and perform that takeoff and descent all the way down to the airport. Now, regions near the ground are known as Class G airspace. There are some surface extensions to Class E, depending upon the type of Class D airport. But for the most part, UAS are operated within this Class G airspace. You'll notice there is this boundary. You're not supposed to be operating other aircraft, manned aircraft close to the ground. And so this does provide you a natural separation between those two. There are exceptions, crop dusting aircraft, helicopters, particularly emergency transport helicopters, tend to operate much closer to the ground. So in that case, it's always incumbent upon the UAS pilot in command to be very, very aware about the airspace that you're operating in. Okay, and so you have to be able to keep an eye on that. And again, you'll notice these natural boundaries that you have that are put in place to be able to protect the aircraft, particularly the manned aircraft that are operating within the airspace. You will notice a couple definitions. We have mean sea level, which defines Class A. All these other altitudes are above ground level. So they're referencing the local ground level. So for example, here we're around 900 feet. So that means we can fly up to about 1,300 feet MSL. We're always going to observe that kind of local AGL measurement. Now, the idea behind this, again, is that it provides you a natural buffer zone between UAS or drone operations and then manned aircraft operations, which is particularly important here at OSU because we have a very busy aviation and pilot school. So it's very common to see very small aircraft operating out of Stillwater. You'll also see pretty commonly aircraft from Vance Air Force Base that use SWO for training. So that's particularly important to make sure that you're following these rules in maintaining that 400 foot and below operating zone, because we want to avoid that. Okay. Now there are exceptions. One of those is flying around structures. So if you have a tower or a building, for example, that 400 foot height limit is from the maximum altitude that particular building or structure with a 400 foot radius around it. So if you want to fly next to a telecommunications tower, which is important for the telecommunications industry, they use UAVs pretty commonly for surveys, things such as wind turbines, or you're doing building structural analysis. You want to fly the Devon Tower, for example, then you can use these rules that allow you to go over that 400 foot AGL restriction. The rationale for that is manned aircraft operators are required to avoid these structures by that 500 foot boundary. So, to be safe, they're not going to be flying close to these either. Keep in mind that when you have something like a tower, however, you also have guy wires, and it's very easy to not be able to see those and accidentally fly into them. So you have to be extra cautious when you're flying these regions. Now, I'm not going to go through the details of aviation maps. These are once you get familiar with them, they're fairly straightforward to read. But if you haven't seen one yet, there are lots of good YouTube videos that go through the process of actually reading an aviation map. But if you're operating at OSU, you have to be aware that we do have a Class D airport that's very near campus. And you'll notice this boundary right here, which is the 5 mile zone from the center of the airport. And so that's that 5 mile exclusion zone. Up to several years ago, before the FAA implemented what was called LANCE, you would not be able to fly within this 5 mile boundary whatsoever. But since most of the airport operations within this boundary are primarily in the pattern, taking off and landing, and then the aircraft pretty quickly get away from the surface, there are regions around the airport that you can actually operate in. So you'll see a map that looks much like this. And so this is the low altitude authorization notification capability. So you'll notice there are little boxes here. Each one of these boxes have an altitude. You'll notice most of OSU campus right here, which you can see in this exploded view, is under that Part 107 rule, 400 feet. But you'll also notice on the approach pattern, or the approach path, going just south of the main runway and north of the main runway, those altitudes are lowered to 150 feet, 100 feet, or 0 feet, depending upon where you're at. And there's some areas which are also 300 feet. So you can actually look this up, faa.maps.arcgis.com. Look at any location in the U.S., particularly around airports, and it will show you what those altitude limits are. If for some reason you do need to fly, for example, hey, we need to do flights over Boomer Lake, then you can go to the Lance website. You can just Google that, and it will tell you how you can go through the process of getting permission, which is usually pretty straightforward. Primarily, that is done through an automated process now. Okay. Another example is to the east of Stillwater, we have the Unmanned Aircraft Flight Station. We have a beyond visual line of sight corridor there that allows us to fly much farther from the PIC. So we have a controller here. We can fly all the way up to this corridor here as long as we have visual observers that are able to see the UAV and then radio that information back should there be an incursion in process. So there are ways that you can, get beyond these rules and expand operation for valid reasons. So with that, I'll talk a little bit about USRI. So USRI was founded in 2015, really to serve as a capability for not just the OSU campus, servicing all of the colleges throughout OSU, but all of Oklahoma. And it was really instituted primarily due to the number of requests that our drone labs were getting from various researchers across campus that said, hey, we would like to be able to use a drone for our research. How do we go through the process of doing that? So founding USRI gave us the capability to help support various researchers and students across the OSU campus in the state of Oklahoma. And we're primarily here really to serve the campus and the state. So I see a number of different examples of different systems that have been developed by USRI research engineers and students over the years. Now, we do have a number of facilities across campus. Most of the USRI research and engineering staff sit at Excelsior, which is at the corner of Willis and McElroy, across from the rugby/Quidditch field on the north side of campus. And so, if you're interested, you can always come by and talk to some of the researchers there. We also have research engineers that sit down in the Discovery building, now the Harold Hamm Institute for New American Energy in Oklahoma City. And we'll pretty soon have researchers at the Helmrich Research Center in Tulsa as well. Really there to be able to serve the surrounding communities and work not just with campus and the state, but also industry. There is a indoor flight test facility at Endeavor, which is open primarily for undergraduate student use if you're interested in indoor flight. And anything indoors, you don't have to worry about all those pesky FAA rules. The FAA only cares about operation outside. So even in a net or indoors or under a tarp, you're free from those rules. Now, we do have a number of flight test assets across the state. As I mentioned, we have the Unmanned Aircraft Flight Station, which is operated by Professor Andy Arena, and we have that beyond visual line of sight corridor that connects that. We work very closely with the Choctaw Nation. They have an FAA UAS test site, which has about 45,000 acres worth of test range for them to utilize. We have a test facility at Fort Sill, which sits under the Fort Sill restricted airspace, but is on OSU property. And then we have a number of other COAs and test ranges across the state. You can see, for example, here, this is our Western COA, which we primarily use for storm chasing activities. And so this goes into the Texas Panhandle and covers most of the western half of the state of Oklahoma. Now, there are a number of things that OSU USRI research engineers do in terms of helping fabricate design systems and go out and test them. And so there are a number of facilities, in addition to the flight test facilities that I mentioned, that are useful for designing, building, and testing aircraft. So, so there are a number of ways to work with USRI if you're interested. Part of that is Part 107 training. We offer every so often Part 107 training workshops. It is a bit of an onerous test if you're not familiar with the material. So, going through a day-long workshop, gives you a really high probability of passing the test. Flight training, so you can learn how to operate the vehicles. Believe it or not, you can get a drone pilot's license in the U.S. without ever proving that you've been able to fly a drone in the past. So we do suggest that you get compliant and comfortable doing different drone operations if you go get Part 107 training. You don't want to be that guy or gal that the first time you fly the drone is when you crash it. Also, flight operations helps supporting operations, custom system design and fabrication, and then data analysis. Our focus always is on making sure that you're using the drone to be able to get your data more easily, more readily, more efficiently. And that's really the end goal, right? If you're not able to do that, you probably want to look at a different option rather than going out and using a drone. You don't want to use a drone for a drone's sake. We do get a lot of calls that from researchers across campus that are essentially, well, I bought a drone, now what do I do? And we always ask, well, is a drone really the right answer for the question that you have first? And then we'll make that determination about how to make it efficient. A drone is just a tool like any other research tool in the lab. I will talk about some sample collaborative projects that we're currently doing, just to give you a flavor of the wide breadth that we have. One of those is the development of what's called a SnotBot, which is from one of our integrative biologist professor here, Jason Brook, who's now at Stephen F. Austin University. But essentially, he's interested in capturing the samples from dolphin, what's called blow, as they exhale. They're exhaling essentially saliva, and capturing that saliva can then be utilized to determine a lot about the dolphin health. And so capturing that is really, really difficult to do. If you pull the dolphins in to a boat, you're not only potentially risking harm to the dolphin itself, you're also stressing the dolphin, which changes the results. You're changing the result of the experiment that you're trying to do. So we have students here that are developing systems to try to capture that directly in the wild. And even though we've been focused primarily on drones, we also do other types of systems, other aerial vehicles such as balloons, maritime vehicles such as boats, and ground systems. This particular boat here has been developed with civil engineering and environmental science faculty, primarily to obtain water quality samples to observe harmful algal blooms that might form in some of the Oklahoma lakes. So this particular system, you'll notice it's nothing more than a simple kayak that you can get from Walmart, but it's integrated with electric propulsion systems, autonomous navigation, and the most important part of this is the payload. That piece is actually acquiring the data, which is what you use to write your papers and get your theses and dissertations. So this just allows you to do that in a much more effective way. So we have a number of faculty, both within the School of Mechanical and Aerospace Engineering, as well as affiliate faculty that make use of the resources at USRI. If as a faculty member, you're interested in becoming an affiliate faculty, just reach out to me. And we also have a number of research staff as well on campus. If you're flying on campus, we do recommend that you go through a unmanned aircraft use request form. This is not really required for OSU researchers as long as you're following the Part 107 rules. But if you're new to this, it does allow us to determine if you need any assistance, and that form is available online. So I'll finish up with some FAQs before we see if there are any questions from the gallery. So first off, as an OSU researcher, do I need a licensed Part 107 to fly my drone? And the answer to that is yes. Either you or someone else, the pilot in command, needs to have a valid Part 107 license. Those licenses do expire after 2 years, and so you have to go back and get that renewed, just like you would your driver's license. So yes, that is required. Every drone pilot or drone operation needs to have a Part 107 pilot. As an OSU researcher, do I need approval to fly a drone on campus? The answer is no, as long as you follow the FAA and campus regulations. So we do have a set of regulations on campus. Primarily, don't do anything stupid. So, don't fly over people. Don't endanger anyone or property on campus. But most importantly, as long as you're following the FAA rules, then that's okay. If I am not affiliated with OSU, do I need approval to fly on campus? The answer to that is yes. You must fill out one of those approval request forms prior to flying on campus. And this is primarily for insurance purposes. And again, making sure that we're keeping not just property, but people on campus safe. Do I need to work with USRI in order to fly on campus? The answer to that is no. You just follow the rules, but we're always here to help if you have any questions about anything. Our role is just to, again, hopefully make your life easier. And finally, if you only fly recreationally, do you need to register your drone? Yes. Per FAA regulations, all drones over 250 grams need to be registered. And you should go through the trust process, which I mentioned earlier. If you go to either of these websites, they will provide you all the information that you need in order to be able to fly your UAS safely. FAA.gov/UAS or knowbeforeyouFly.org. They'll provide you not only the resources you need to be able to get your Part 107 or your recreational license, but also register your drone at the FAA Drone Zone. Finally, I'd like to end with just a comment. This is an example from one of our flights many years ago when we were working on a NASA project to develop aircraft for eventual flight on Mars, which we've done now. And so not we personally, but we as mankind, right? We've flown aircraft now on another planet, which is pretty amazing. It's a drone that flew on Mars completely autonomously. As we were going through these testing, we went from a relatively low altitude, like in Oklahoma, up to Colorado, where we're going to be doing our high altitude flight tests. The aircraft are going to be borne aloft by a high altitude balloon and then drop down to replicate the environment that you would see on Mars. And one thing we noticed when we started flying, we would take off manually and we put the aircraft into autonomous mode. And every time we did that, it went from a straight and level flight and then nosedived into the ground. First time we did that, we thought it was an aberration. Second time we did that, we thought, well, that's just a fluke. And third time we did that, we thought, well, we're obviously doing something wrong. And initially we thought there was something wrong with the autopilot, but what the autopilot was doing was exactly what we were telling it to do, which was fly to the altitude here in Stillwater, not the altitude that it was at in Colorado. Very, very simple human error, right? And the most common source of accidents, not just in drones, but all aviation, are due to human error. So it is important that when you fly drones, you are thinking like an aviator. You have a dangerous aircraft operating in the airspace, which could result in serious damage to either people or property. So think about safety first. If you think it's going to be something that might potentially result in an accident, don't do it. Okay. And with that, here's contact info. Feel free to reach out if you have any questions. And I think with that, we'll go to questions from the audience.
And you can feel free to unmute yourself or type your questions into the chat.
Yeah, it looks like most of the questions I see now are just based upon the recording sent out. And I believe that, yes, this will be sent out at a later date for those who are not able to attend in person.
Thanks so much, Dr. Jacob. I do have a question. And I suppose this is an issue with all of our smart devices that are collecting more and more data and higher resolution relating to privacy. And if there are any conversations on
Yes.
balancing the need to and the value of collecting all of this data with protection of privacy.
Yeah, and that's a great question. Again, we could have a whole discussion just on that. I was given a talk to the Department of Geography earlier this week, and one of the faculty there asked that, and it's really a balance between what are known as First and Fourth Amendment rights. Your right to essentially free speech and your ability to see the public around you, and your right to a reasonable expectation of privacy. And so there's a lot of discussion about this. The good thing is the systems become more automated. You start to have that ability to automatically say, well, here's property over here I shouldn't be looking at. So I need to focus on, the data that I need to observe. But it is something that every researcher, as you're thinking about these systems, you should be thinking about them in the same context that you would if you were getting approval to use a laser on campus, or approval for using personal data through an IRB or animal testing. You should think about the same process. We don't have those set up now. We might in the future, where you have to go through a similar type of process to be able to use a drone remote sensing. The tools are still too new right now that we're not even quite sure, how to approach that from an ethical standpoint. But that's a really thorny issue, particularly at the state legislature level. Making sure that you're maintaining privacy.
Thank you very much.
And I do see a question about how frequent do we offer training workshops. The training workshops themselves, we normally do not charge for. But if you send me your info, I'll put you on the list to make sure that when we do offer another Part 107 workshop, we'll have you included on that. We do plan on offering one in the fairly near future. We're a little bit behind where we'd like to offer one, but we've just been overloaded with a lot of work, so we haven't been able to take out the time to go through the process of offering one of those workshops. But just please feel free to send an email to the usri@okstate.edu, and we'll make sure we have you on the list for when we offer that next.
Hi, Jamie, this is New One. Very good talk.
Oh, thanks. Hey, Ning, how you doing?
Good. We have this custom built drone. We need to register it. We tried it before, but because it's kind of complicated compared with, if you buy a drone, it's really easy. Just put a serial number there and then you can register it. But once you build one, you bought all the parts on and put them together as a drone. So how do we register?
Yeah, we haven't had any problems because we do registration of a lot of our custom systems pretty regularly. But I will email you our contact info for our engineer who handles all of our registration, and he can help you out with that.
Yeah, we definitely need to do that. Okay. We haven't. Yeah. Thank you.
Hey, you're welcome.
Mm-hmm.
All right. With that, I think we'll close it out. Thanks for your time today.
Thank you very much.